This is problem 30.4 and it deals with Faraday's law. We're told that we have a long solenoid with N is equal to 400 turns per meter and it carries a current given by I is equal to 30. Then here we have 1 minus e to the negative 1.6 t. This is saying that I is time dependent, right? Time is right there. I is in amperes, t is in seconds. Inside the solenoid and coaxial with it is a coil here that has a radius r is equal to 6 centimeters and consists of a total of N is equal to 250 turns of fine wire. What EMF is induced in the coil by the change in current? So let's just think about this for a second. We're told that here the current's kind of like coming out of the page here and it's going into the page. So we use our second right hand rule and we see that this is going to give us a magnetic field that we know to be uniform along this axis in this direction here. We know that for a solenoid, B is equal to mu naught N times I. We've done this before in other problems. So we can just go ahead and write out what B is. So we have B is equal to mu naught is just 4 times pi times 10 to the negative 7 newtons per ampere squared. Little n is just 400 turns per meter, and then the current is 30 amps times, and then 1 minus e to the negative 1.6 times t. Where here, this 1.6 has units of inverse seconds. We can make this a little bit prettier, move things around, and we get V is equal to 1.51 times 10 to the negative 2 newtons, amps per meter, and then we have 1 minus e to the negative 1.6 times t again. Now we know that B changes with time because here, this component changes with time. It's dependent on time. So because we have a changing magnetic field, we are going to have a change in flux, and because we have this change in flux, that is going to induce an EMF. That is essentially the law we're talking about. That's Faraday's law, where EMF is equal to negative d5b over dt, right? Well, here we have an n right before it because we have multiple loops in this little thing down here, right? We're inducing this current inside of this loop here. So let's calculate 5b, where 5b, the flux, is equal to the integral of b dA cos theta. Here we have B, our magnetic field, is parallel to dA because we're trying to figure out what is the flux going through this little loop here that has radius 6 centimeters, and we know that the magnetic field that's going through it is the magnetic field that is caused by the solenoid itself, right? So we know that, and we know that here B is in this direction, dA is in this direction. It's all facing one direction too, so that makes it really easy for us. So then we say that cos of theta is equal to 1 because they're parallel to one another, and then 5b is just equal to b because b is uniform, integral of dA, and that is just going to be equal to b times pi r squared. We're just saying, well, what's the area, right? What's this area specifically? Because again, we're trying to figure out what is the current induced in this loop here. So that's what we have, and now we know the big R, that's just equal to 6 centimeters. So then we have 5b is equal to, we know what b is, it's this, so 1.51 times 10 to the negative 2 Newton amps per meter, and then we have 1 minus e to the negative 1.6 times t times pi times 0.06 meters squared. If we make this prettier again, so just like add up or multiply all the numbers together, we get 1.71 times 10 to the negative 4 Newton amps per meter, and then we get this factor as well. Okay, so that is the flux. Now we want to know this. How does the flux change with time? So all we have to do is take the time derivative of the flux, which is pretty easy because t is only up here. So then we say E, the EMF, is equal to negative n times d phi over dt, where I'm just going to move this over down here. d phi over dt is equal to, and then we have the constant stays the same, so it's just going to be this, 10 to the negative 4 Newton amps per meter. And then here we're taking the derivative, so I mean this goes away, right? And all we have is here, we take the negative 1.6, we bring it down, multiplies by this negative sign, so it's positive. So then we get 1.6. And I told you at the beginning that this has units of seconds to the negative 1. And then we have e to negative 1.6t. That stays the same. All I did was take the derivative. And then we have to multiply this by negative n. So here we multiply that by negative 250, right? Because that's how many turns we have. So this is E, the EMF. And if I do the math, so I multiply this by this by this, and I cancel out all of my units, I get 0.06832 volts times e to the negative 1.6 times t. So that's going to give me about 68.3 millivolts e to the negative 1.6 times t. The units are important here because we know an EMF has units of volts. I should make this clear, this is an 8. And then here this has units of per second, this is units per second, units cancel out, and my answer is just going to be something in millivolts. Okay, so that is it for this question. All they wanted us to do was figure out what was the EMF that was induced by this change in current here.